Right, we've reached video number 10 for AI. Yay! So the last thing I want to talk about under the heading of CSPs is the idea of backjumping. Now I've already mentioned briefly what I mean by this. The kind of backtracking that you're by now very familiar with is generally known as chronological backtracking. And with chronological backtracking, we just backtrack one step and try an alternative. But I have a very straightforward example here that shows that you may actually be able to do better than that. The left of this diagram has our running example, and on the right I've drawn it in a slightly different way, which is a little bit more amenable to talking about backjumping algorithms. So on the right I have essentially the same graph, but drawn in order to emphasize the order in which I'm making assignments to variables. So the upward arrows here indicate the fact that I'm assigning variable 1, then 3, then 5, then 4, and now I'm thinking about what I could assign to 7. And the non-arrowed arcs are edges from the graph indicating constraints. Now the key point here is that if we've assigned things in this order, 1 is B, 3 is R, 5 is C, and 4 is B, and now we want to assign something to 7, we can't, because it's connected to 1, 3, and 5. They have the 3 different possibilities, so there's no possibility left for 7. Now, with chronological backtracking, we would backtrack one step and try and reassign 4. But a short consideration of the situation we have makes it very obvious that reassigning 4 will make no difference to the fact that we can't assign anything to 7. And the reason that is simply that there is no constraint between 4 and 7. The fact that we can't assign anything to 7 at this point is entirely to do with the fact that it has constraints with 1, 3, and 5, so reassigning 4 can make no difference at all. And that means that in this example, we could backjump as far as the assignment to the 5th variable, to variable 5. So what we want to do now is look at this kind of process in general. How do we do the bookkeeping so that we can jump back multiple levels at once without sacrificing the ability to find a solution? Okay, and by that what I really mean is without actually missing any possibilities. Now, in thinking about this a bit more rigorously, we do unfortunately have to get into some somewhat gnarly notation. And that's a pity, because the 2 versions of backjumping that I'm going to show you are fundamentally fairly straightforward. It's just really unfortunate that they're quite tricky to write down. So what I suggest you do is look at the examples, think about what's going on, and then come back and try to follow through the notational, the rigorous version. Because I think with this kind of algorithm, by understanding how the examples are working, which is relatively straightforward, it makes it a lot easier to understand the rigorous version. So I have 4 initial points here regarding new notation. Point 1 just says that variable left arrow D is how we will represent an assignment. Okay, so if we have the ith variable and some value D in its domain, an assignment A is just vi left arrow D. The second point is that a partial instantiation is just a bunch of assignments that are consistent. Now, when I say the first k variables here, I don't necessarily mean variables 1, 2, and so on up to k. What I mean is the first k variable assignments in whatever order we're making them. The third point is just saying that we want our partial instantiations to be consistent, in the sense that none of the assignments in a partial instantiation breaks any of the constraints. And the fourth point here is simply that we will say that a partial instantiation conflicts with some variable if there's no value left for that variable that's consistent with the partial instantiation. Now there's a slight notational difficulty here, which is that so far I've labelled variables as being v1, v2, v3 and so on up to vn. Now I have to talk about assigning variables in a particular order. Now in order to do that, I'm going to do something a bit naughty and change the notation. So now I'm assuming that variables are assigned in order v1, v2 up to vn. So the subscript now denotes the ordering in which I assign variables, not the identifying number for the variable itself. Saying I assign v1 first means simply that this is whatever variable I am assigning first. It could be any of the actual variables. And similarly, v2 denotes whichever variable it is that I assign second, and so on. Now the first approach to backjumping I want to introduce is called Gaschnig's algorithm, and this is really very straightforward indeed. Now if we've got a partial instantiation of the first k variables that we assign, and now we want to assign the k plus 1th variable, we need to check that any candidate value that we're going to assign to the k plus 1th variable is consistent with the partial instantiation. Now when we test potential values that we could assign here, we will generally discard one or more of them because they'll be in conflict with something in the partial instantiation. And Gaschnig's algorithm just keeps track of the most recent assignment for which that's happened. Now as usual, if there is no value that we can assign to the k plus 1th variable that's consistent with our partial instantiation, then we have detected the fact that we need to backtrack, or hopefully backjump. And formally speaking, the point that we backjump to is given by the single equation on this slide. So what does this say? All it says is that we backtrack to the most recent variable that we assigned in the partial instantiation that has a conflict with the k plus 1th variable. The question then arises, of course, of what happens if we backjump to the jth variable using this equation and it has no values left. Well, in that case, Gaschnig's algorithm then just reverts to backtracking chronologically. Here's a simple example once again. We've assigned variable 1, then variable 3, then 5, then 4, then 8, then 2, and now we want to know if there's something that we can assign to 7. And at this point there isn't. Now if we look at what's happening here, as we go up the sequence of assignments, starting from variable 1, in assigning variable 1 to be b, we remove that possibility from 7's domain, because 7 has a constraint with 1. And then in assigning 3, we remove the next one. In assigning 5, we remove the next one. And at that point, 7 has no possibilities left. Now at the point that we've assigned variable 5, the partial instantiation has become inconsistent with the 7th variable. And as we go further up the chain of assignments, it remains inconsistent with the 7th variable. However, at any point prior to assigning variable number 5, the partial instantiation is still consistent with variable 7. So 5 is the point that we backtrack to. Now it's clear that Gaschnig's algorithm has allowed us to make some progress. When we first find that we've got to a variable that we want to assign and there are no possibilities left that will work, we can do potentially a backjump over more than one variable assignments. And we can do that without adversely affecting the search process. The question now is, can we do better if we then have to make a further back jump? Because after the first one, we come to a variable which then in turn has no usable values left. Can we now do a further back jump rather than doing what Gaschnig's algorithm would do under those circumstances, which is just to revert to chronological backtracking? So, we need a little bit more nomenclature here. If I've got a list of variables that have been assigned, k of them, v1 up to vk, in a set, in this case v prime, and I am interested in assigning something to the k plus 1th variable, I define the ancestors of the k plus 1th variable to be the subset of variables 1 up to k that have a constraint with variable k plus 1. And the parent of the k plus 1th variable is its most recent ancestor in the sequence of assignments. Graph-based backjumping does something pretty obvious. It backtracks to the parent of the k plus 1th variable. So here again, the simple example, what's being illustrated here is the way in which the graph on the right is built up as we make a sequence of assignments. And at each point I've annotated on the right the ancestors of the corresponding variable. So initially I assign 1 and then 3. Now 3 has the predecessor 1 and it has a constraint with it. So 1 is an ancestor of 3. Similarly, 3 is an ancestor of 5. And so on. And it gets interesting up at the point where we assign something to variable 2. Its ancestors are 1, 3, 4, and 8, because those are the numbers of the variables in the preceding assignments that have a constraint with variable 2. Now, at the point that we get to assigning variable 7 and we realize there are no possibilities left, we look at its ancestors and we take the most recent one in the sequence. The most recent assignment in the sequence out of variables 1, 3, and 5 is variable 5. So that's the one that we backjump to. Backjumping and forward checking appear to have something in common. So we're trying to assign something to the k plus 1th variable by making it equal to some value d. With forward checking, we would remove d from the domain of all the unassigned variables vi that are connected to the current one by a constraint. This is very similar to what we're doing with graph-based backjumping, because in this case we'd also add the variable that we're assigning to the list of ancestors of the currently unassigned variables vi. Now, it turns out that forward checking can make some forms of backjumping redundant. And in fact, one can go further than I'm going to go in these lectures and combine constraint propagation with backjumping in order to get more interesting algorithms. There's a lot more that could be said here. Unfortunately, once again, I don't have time. If you wish to read up more on this kind of algorithm and the places that you can go with it, take a look at Dechter's textbook, which I gave you the reference to in the introductory lectures. But for now, I'll just give again a simple example of the interaction. Here we've got, once again, the simple running example. We have on the right a sequence of assignments and a list of ancestors for the variables at the point that we've got to in the illustration. And in this example, forward checking clearly establishes that we have a problem in that we're not going to be able to finish off our sequence of assignments earlier than just looking for a backjump does. Because it establishes at the point that we assign variable 5 to be C that 7 has no possibilities left. Now what that's given us is essentially a second, arguably simpler method for doing the first back jump. But we still haven't answered the question of what then happens if we want to do a second back jump rather than reverting to chronological backtracking. Now we can't just extend the idea of making a back jump to a parent in the obvious way. We can't just back jump once, realise that the variable we've arrived at has no possibilities, and then try to back jump to its parent. This isn't going to work. In the illustration here, on the left, I have a sequence of assignments. I've come to the 7th one and realised that I can get no further. So I back jump to its parent, which in this case is the 4th variable in the sequence of assignments. And that's fine. That's exactly the process that we've just looked at. Now, let's say that the 4th variable in that sequence has no possibilities left for it. Can we just back jump to its parent? Now, its parent would be v2, the 2nd variable in the sequence of assignments. But that gets us into danger. And on the right, I've tried to illustrate precisely why that is. If we're interested in what happens at v4, having back jumped there and having found that there's nothing left we can try, back jumping to its parent would take us back to the 2nd variable v2. But if we look at the arrangement of constraints in this sequence, v3 has a constraint with v7. And here's the key point. The fact that in the first place we had no possibilities left for v7 may have been due to the fact that it has a constraint with v3. So by trying an alternative for v3, we may then be able to move forward, get back up as far as v7, and then be able to make a successful assignment there. So, in summary, if we get to v7 on the left, we can back jump to its parent, v4, and this is fine. But we don't want to just apply the same reasoning again, because it's possible that by changing the assignment to v3, we could fix the problem that initially made us back jump. And by back jumping over v3 to v2, which would be the naive approach, we can miss this possibility. So how do we now get around this? Well, the description in this case is a bit more involved. So I apologise for the continued introduction of new notation, but unfortunately it is necessary. Firstly, we need the idea of a leaf dead end variable. So, on the left, we have a situation where we've got a partial instantiation containing v1 up to v6, and we're interested in assigning to the k plus 1th variable v7, and there is no consistent value that we can give it. Now in this case, the partial instantiation is called a leaf dead end, and the variable that we don't have any assignments for is called a leaf dead end variable. So in this case, the leaf dead end is the collection of variables v1 up to v6, and the leaf dead end variable is the variable v7. Now, the leaf dead end variable, in this case v7, is the key one that we're initially backtracking from. If we've got a variable that we backtracked to and it has no more values, we call this an internal dead end variable. And the partial assignment leading up to that internal dead end variable is called an internal dead end. So in the running example, on the right, we've backtracked from v7 to v4. That makes v4 an internal dead end variable, and it makes the sequence from v1 up to v3 an internal dead end. And we still need some more definitions. The session for some variable begins when the search algorithm visits it and ends when it backtracks through it. And the current session for a variable is the set of all the variables that get visited during its session. The relevant dead ends for a current session for some variable v include v itself, and that's how the relevant dead ends for v are initialized when v is first visited. If v is a leaf dead end variable itself, then its relevant dead ends only include itself. But we can accumulate relevant dead ends because if a variable v is backtracked to from some other dead end, then we accumulate both collections of relevant dead ends together. One collection from the variable we backtracked from, and one collection from the variable we backtracked to. Here is an example again. On the left, we're looking at the relevant dead ends for v7. Now v7 is a leaf dead end, so its session is just itself, and its collection of relevant dead ends just includes itself. On the right, the session for v4, which is where we're backjumping to, contains all of the variables visited between v4 being visited and backtracking through v4. So it includes v4, v5, v6 and v7. Now the relevant dead ends for v4 are initialized to be only v4, but when we backtrack from v7, we collect together v4's relevant dead ends and v7's relevant dead ends, which updates the relevant dead ends for v4 to now include v4 and v7. And this is the last set of definitions that we're going to need. The induced ancestors for some variable, vk, are a subset of the variables that were assigned before vk in the sequence. So here we've got ind vk equals the set v1, v2 up as far as vk minus 1, intersected with, okay, so we're going to take a subset of those. Well, what do we have here? This is the union for the variables v in the relevant dead ends of vk of the ancestors for those variables. Now we'll continue with the example in just a moment, which hopefully will make that look a lot clearer. The culprit for vk is the most recent variable in the sequence of assignments that's in the induced ancestors of vk. Now, if we've backjumped once already and we want to do a further backjump, we backjump to the culprit. And here is our running example. We backjump initially from v7, and we find that v4 has nothing left to try. The relevant dead ends for v4, as we established earlier in this example, are v4 and v7. The next step is to take the ancestors of v4 and the ancestors of v7. v4 has only one ancestor, and that's v2. v7 has ancestors v4 and v3. We take the ancestors which precede the variable we've backjumped to in the sequence. That gives us the induced ancestors for v4, which is the collection v2, v3. And our second backjump takes us to the most recent of those, which is v3, and that's exactly what we're hoping for. Now in this case we didn't get a second backjump, we got just essentially the equivalent of chronological backtracking. But if you like, you can use it as an exercise to construct an example where you'll get a second backjump. Now, the last thing I want to point out about constraint satisfaction problems is, well, as promised, when I started talking about them, I said I'd mention that there are other kinds of CSP beyond discrete CSPs with finite domains. Now, discrete CSPs with infinite domains might, for example, allow you to assign variables to be integer valued. If your domain is all integers, then clearly it's an infinite domain. And now you would want to introduce a language for describing constraints using, for example, arithmetic operators and inequalities. For integer variables and linear constraints, there are algorithms that can solve these, but for integer variables with nonlinear constraints, in general, there is no algorithm. With continuous domains, you might, for example, allow variables to take real values. And in this case, if you've got linear constraints, you're defining convex regions, and that gives you linear programming, which turns out to be solvable in time polynomial in n, the number of variables. And you can take this further. You can introduce preference constraints, so you can introduce constraints that you would like to be obeyed, but which aren't absolutely necessary. And you can introduce the idea of an objective function which measures how close you are to obeying all your constraints, and you can look at an assignment of variables that in some sense optimizes your objective function in the sense that it gets as close as possible to obeying all possible constraints, and so on. But alas, that is all I have time for on the subject of CSPs.